and also share my screen. So let's get going then. Yeah, so thanks for joining this call. I mostly intend to have this call because I saw that there was a lot of confusion around how repository sizes can be calculated on the Gitaly side and what clients should actually pay attention to when they want to calculate repository sizes. Because there's multiple different ways to actually calculate them, and also there has been a ton of confusion around how repository maintenance is performed in Gitaly influences repository sizes. In case you have any questions during the presentation, please feel free to just speak up and ask them right away. Roughly speaking, I intend to have this meeting roughly split in two phases, where the first half of the meeting should be about a short primer on low-level repository details, and the second half of this meeting is mostly about any additional questions that you have. So topics that I want to talk about right now, there's basically three different things that I want to talk about. The first one is the low-level Git object database, how Git actually stores data on disk. The second one is repository maintenance, so how both Git and Gitaly perform repository maintenance and what impact it does have on the size calculations. And the final one is the size calculations itself, so which methods you have available to calculate the size of a repository. First, with regards to the object database. So, I mean, I guess that most of the things I say here are not really new to you, but I still want to repeat them so that everybody's on the same page. So the Git data itself is stored as objects, where Git knows 4 different types of objects: blobs, trees, commits, and tags. Where a blob is simply like a file, for example, with its contents. A tree is the directory structure. A commit ties a roots tree, so all the directories and blobs referenced by those trees, to a commit message and a commit author. And then we finally have tags, which allow you to put arbitrary names onto commits with additional metadata. And each commit uniquely identifies all blobs as well as all the trees and all the history before it, because we actually have a tree structure with the hashes that they form. Like a commit references a tree again references other trees, and may also reference blobs. And with this, we in the end end up with a tree structure that really allows us to walk history and to see which references or which objects are referenced by each of the commits and trees and so on. The objects are stored in the so-called Git object database, or ODB for short, and this is actually a content-addressable file system, where content-addressable simply means that the address of an object is calculated by hashing its contents. You can see this on the right-hand side. So we first initialize a repository, then go into it, and then we can, for example, hash an object by saying git hash object -w-stdin, which simply means please hash the contents from standard input and write it into the repository. And then we see that we get a hash, which is this D95F3 string and so on. And this is actually the address of that object. And the object can again be looked up by saying, or by using that hash, for example, by saying git cat file-p and then the hash of that object. So this is what is called a content-addressable file system. So how do those files actually get stored on disk? The first mechanism that Git has is the more pragmatic approach, which is simply loose objects. So each of the objects is initially stored as a loose object, which are simply plain files inside of the .git/objects directory. So again, you can see on the right-hand side, after we have written the object into the object database, and then if you do a listing of the objects directory inside of your Git repository, you see that we have the exact address of that object in D9 and the D9 folder, and then afterwards we have D5, F3, and so on. So this is the actual object, and the content of that object is zlib compressed. So it's not directly written to disk in plain contents, but it's really compressed first. But one important thing to notice here is that each of the loose objects actually contains the full data of that object. So if you, for example, do a simple change to one of those objects or to the same file, it would be stored as 2 different loose objects, but each of them contain the full data. which also means that the storage size would actually be duplicated in this context. Which also means that storing all objects as individual files is actually quite expensive because, well, every loose object would require an inode. Every loose object contains the full data, and also accessing all the loose object would require us to open many different files. And you can see, like, if you have a repository with millions of objects, that this is actually quite expensive. So you actually don't want to do that. And instead, you want Git has another primitive to store files or objects inside of the object database, which is so-called Packfiles. So in regular intervals, Git actually takes all the loose objects that you have in the repository and compresses them into a Packfile, where the Packfile itself contains like not only a single object, but actually many objects. So this has multiple benefits. First, you have all the Packfile, all the objects contained in a single file, so you have less inodes, you have less files to open, you don't have issues with open file descriptors and so on. But second, you also have the very important improvement that you can store objects as deltas of other objects. So again, taking the example that you have a single file and only do one change to that file, you wouldn't store both files completely in the Packfile, but you would only store the first file, like the original version of that file, and then the change you did to that file would only be stored as the so-called delta, so that you can significantly compress or avoid having to store like the complete size of the objects. And this is a whole lot more efficient than actually storing them on loose files as loose objects. Furthermore, Packfiles can also have a different metadata attached to them, which is required to speed up various different actions. Like you can see here again on the right-hand side that we first perform a repack by saying git repack -geometric equals 2 and then -d, which simply asks Git to repack all the objects that exist in the repository into a single Packfile, and also delete all the loose objects while at it, which have just been packed into the Packfile. So you can now see that on the right-hand side you have this pack, which is also identified by a hash. And you can see that it actually has 3 different files: an index, which is used to index into the Packfile to be able to efficiently look up an object inside of the pack. Then you have the .packfile, which is the Packfile itself containing all the compressed object data. And then you have the .ref file, which is a reverse index, which is also used to speed up certain operations. For example, if you want to efficiently calculate the size of an object stored inside of the pack. So the thing is that during normal operations, you add loose objects or more Packfiles to Git repositories over time, which also means that they will become significantly slower over time because, well, as I said initially, if you have hundreds of thousands of loose objects inside of the repository, it's slow. Or also if you have like dozens of Packfiles inside of a repository, it's eventually going to become slow. So we have to do repository maintenance regularly to optimize the repository, where Git really knows to do different kinds of repository maintenance to optimize all of the different data structures. So the first one is to compress loose objects into Packfiles. The second important one is to repack Packfiles into less Packfiles, typically only a single Packfile, for example. Prune unreachable objects, which are not referenced by your branches anymore. Compress references if you have a lot of references, and also update caches and metadata so that overall the repository is more efficiently served. In the Git world, you typically do this by executing git-gc, which has a bunch of heuristics to determine which parts of the repository to optimize. Like if there's too many loose objects, it will compress them. If there's too many Packfiles, it will repack them. If there's too many loose references, it will compress them into the packed.res file. And you can see this happening on the right-hand side, where it really does a bunch of things, where I won't really go into the detail of what it's actually doing. Typically, though, you don't really have to execute that command automatically because or manually, because Git does it automatically for many commands. Like if you, for example, do a rebase, then Git knows to automatically call git-gc -auto afterwards, which will perform maintenance as required in the background. The thing, though, is that this doesn't really make a lot of sense for Gitaly itself, because git-gc is not really good fit for server-side maintenance. It has multiple issues here, because first, it's hard to observe. As you saw, it does multiple things at once, and we don't really know what it's doing and why it's doing them. The heuristic it uses are kind of set into stone, so we don't really have a lot of control over what it's doing. It does not use the latest features, like, for example, things that have recently been added to Git to make it more efficient to serve repositories might not actually be updated by using gitgc. And also, it does not really work well with large mono repositories because, again, it doesn't use all the latest features provided by Git, which overall means that we actually implement our own repository maintenance strategy in Gitaly and don't really use gitgc at all. So the Gitaly way is to use optimized repository, which performs all maintenance tasks inside of a Gitaly repository. So again, repacking objects, deleting unreachable objects, compressing references, and updating caches and metadata. And it again uses certain heuristics to decide which parts to actually optimize. And also those heuristics scale with the repository size, which is something that we do to specifically cater to large mono repositories. That means the larger a repository, typically, the longer it takes before we actually start to optimize something, because, again, the larger the repository, the more time it typically takes to optimize those data structures. Furthermore, Gitaly also uses geometric repacking and Cruft packs to pack objects more efficiently, which is, again, something that is especially important in the context of mono repositories. So first, what are geometric repacks? As I said, repositories typically grow pack files over time, where we add more and more and more pack files to the repository, which makes the object access gradually slower. The thing, though, is that in the old world, like previous to optimized repository, Gitaly typically said, like, OK, if there's too many pack files, we'll compress them all into a single full pack file. But this takes a very long time for large mono repositories, like typically on the order of many minutes, if not even hours. And doing that multiple times per day is, of course, very inefficient. So by using geometric repacking, we instead only repack a subset of pack files, like you can see on the right-hand side. Each pack file here is indicated by a square, where the number inside of the square indicates how many objects they have. And with geometric repacking, we try to ensure that we have a geometric sequence of the number of objects inside of the pack file. So on the right-hand side, you have, like, for example, at the top, you have 7 different pack files. And the first 2 actually violate the geometric sequence, because you can see that one is not forming a pack file with a single object is not twice as big as the next biggest pack file. So what we do in this case is that we say, OK, how many pack files do we actually need to repack so that the geometric sequence is again restored? So in this example, we take the first 4 pack files and then compress them into a single pack file again and repack all those objects, so that we end up with a single pack file that has 7 objects to again restore the geometric sequence now. So this takes a whole lot less time than repacking all the pack files into a single pack file again. The second mechanism that we use on the Gitaly side is Cruft packs, and this is also quite important in the context of repository health calculations. Part of the repository maintenance is to prune unreachable objects. But pruning unreachable objects is actually kind of hard to do, because you cannot prune objects immediately, because there could be race conditions with concurrently running processes. Like if there's a process, a Git process that is currently trying to access a specific object, and that object is being pruned at the same point in time, then it could end up with repository corruption. So what you're doing in a Git repository is typically to have a grace period, where you say only if the certain object has not been accessed or is not referenced for a certain amount of time, only then will it actually be cleaned up. Historically, unreachable objects were stored as loose objects, which has the nice benefit that you can use their end time as an indicator for this grace period. So you simply check, like, OK, what is the last time that the object was actually accessed or modified? And if that is older than the grace period, then we are safe to delete it, also if it's unreferenced. But nowadays we actually use Cruft packs instead, where instead of evicting loose unreachable objects instead of evicting unreachable objects into loose objects, we will write them into a Cruft pack first, which has the benefit that this is a whole lot more efficient to actually store, because, as we saw multiple times already, storing data in pack files is more efficient than storing them as loose objects. And this pack file is accommodated with a metadata file, which stores all the different access times of those objects inside of the Cruft pack. Now, The strategy that we use in Gitaly to perform maintenance and to repack objects is basically a 3-step strategy. First, we check whether the last full repack is more than 5 days old or more than 5 days ago. If it is, then we perform a full repack and rewrite all the objects inside of the repository. Also compute the reachability and depict all unreachable objects into a Cruft pack. If there's too many pack files, then we perform a geometric repack so that we have less pack files afterwards. And finally, if there's too many loose objects, we simply create a new pack file by compressing all the loose objects into the new pack file. And this again has implications for calculating repository sizes, because the only point in time where we actually evict unreachable objects into Cruft packs is when we do a full repack. This it means that we only perform it after 5 days. And this means that 5 days is the minimum amount of time before we actually label an object as unreachable and put it into a Cruft pack. And then to actually delete such an object from the repository, we will have to wait another 5 days because it needs the second full repack. So together, this means that in order to delete an unreachable object, it takes around 10 days, which is also something that has been causing quite a lot of frustration in the context of customers, where they say, like, look, I have just rewritten my repository, but still the size of the repository is not updated. And this is actually because, yeah, it takes some time to actually repack. They can use some UI interfaces, for example, to manually repack the repository and then afterwards manually prune objects, but this is quite complex for customers. So this brings me to the different ways you can perform repository size calculations in a repository and the different ups and downs. The old way how we perform repository size calculations in a repository is with the RepositorySize RPC. What this RPC does is simply take the complete on-disk size of the repository. So you essentially simply execute du on the on-disk repository and say this is your repository size. It has the significant upside that it's actually very fast to compute, but it also has a bunch of downsides because it includes caches and garbage, like all the metadata that we have and that the customer has no control over. All the different caches, they would actually be accounted for. And this is typically not really totally fair to the customer because they have no control over it. Also, it could be that, for example, if we have bugs in Gitaly where we started writing garbage by accident into a repository, which has happened multiple times in the past, this garbage will also actually be accounted for in this repository size RPC. Second, because it only takes the on-disk size, it will also include all the unreachable objects in the repository. It may double count objects if they exist, for example, in multiple pack files, or if they exist as in the pack file and as a loose object. And another very significant downside of this RPC is that the repository size may double during maintenance, because when we write the new pack file, we first have to write the complete new pack file containing all the objects inside of the repository, and only afterwards can we actually delete the old pack file, which means that during the repository maintenance, it can actually be that the repository is twice as large, and we would report that doubled size in this RPC. And last but not least, it also does not include the size of object pools, because if you have an object pool, then the objects would typically be deduplicated. So the actual main repository is basically empty because it only has objects that are unique to that specific fork, and all the other objects which are contained in the object pool would be deduplicated. Those would not be accounted for in the repository size RPC. So this RPC is not really a great fit to actually do anything that would regard a customer. We have introduced an iteration of that RPC in Gitaly, which is the RepositoryInfo RPC. It provides finer-grained information about specific data structures in the repository, like you can see on the right-hand side. You have specific information about the references that exist on the repository. You have specific information about the objects, and we also discern reset objects. We discern stale objects, which is done by using Cruft packs as a heuristic. So recent objects are all those objects which are not part of a Cruft pack, and stale objects are all those objects which are part of a Cruft pack. It again has the upside that it's still very fast to compute because we only do on this size calculations. It can discern Cruft objects, and it also does not include caches and garbage because we actually don't count them in the object size, for example. But it still has a few significant downsides here, like unreachable objects are only updated every 5 days because of exactly the way we recalculate the Cruft packs only every 5 days. It also could still double count objects if they are contained in multiple Packfiles or in a Packfile and a loose object. It's also still prone to the size doubling issue that I talked about in the context of repository maintenance, even though it is less likely in this case because the new Packfile will first be written as a temporary file, and that one would not be included in the RepositoryInfo RPC. But still, the size could still be doubled if you're very lucky and hit a specific race condition. And last but not least, it also still does not include the size of object pools because it only goes to that one repository. Which has led to another iteration on how to calculate the object size in a repository, which is the ObjectsSize RPC. This is significantly different from the other two RPCs because what it does is to calculate the repository size by doing an actual graph walk. So you really take a set of references or revisions and walk down all the commits and all the files reachable from those revisions, which means that you actually can specifically choose which objects to include and which objects not include. So you can really freely choose here. Which would give you a whole lot of flexibility. Like you can say, I want to exclude internal references. Like, for example, we have merge request references, we have keep around references that the customer cannot control. They cannot even delete those references, which again means that we might actually want to exclude them, for example, in the repository size calculations. And we can do this by using this RPC. Also, it is possible, for example, to say, I only want to calculate the size for new objects. I only want to calculate the size for a single blob or for a single commit, whatnot. You really have a whole lot of flexibility in how to handle this RPC. And you can also even say that you want to optionally include or exclude the size of the object pool. But it has a very significant downside in this context because it is orders of magnitude slower compared to both RepositorySize and RepositoryInfo. And we're really talking about multiple orders of magnitudes. Where the previous RPCs would return in a few milliseconds, object size can take seconds and even multiple minutes. And I even saw it once to run for more than half an hour in a very, very large repository, which is basically because you have to walk the complete object graph of the repository, and this can take a very significant amount of time. There are, as I said, there's multiple different use cases you can use it for, and I've listed a few of those use cases here by specifying the revisions you can pass to it. You can again say, I want to have all reachable objects by just passing --all. You can have all branches and tags by saying --tags --branches. Single references by giving the reference name itself. Can list only new objects by excluding all the existing references that exist in the repository by saying --not all and --all. And then including all the new object IDs. You can also exclude or include object pools by saying --alternate refs. And those also account for object pools in this context. So there really are three different ways to perform size calculations inside of the repository right now. And here I have a short summary of what the upsides and downsides are as well as the recommended use cases. Repository size, I would say you should actually never use it because this RPC is going to be deprecated and will be removed in favor of RepositoryInfo, which also has all the information that RepositorySize actually currently surfaces. It has the upsides that it's fast to compute, but on the other hand, it really only has downsides because it's not flexible at all, and it really only gives the complete repository size. RepositoryInfo has the advantage that it's, again, still fast to compute and also while also not taking into account garbage and metadata and so on. And it also gives you an ability to discern stale objects in the context of Cruft packs. But again, stale objects are only updated on a full repack, so only every 5 days. It does not include object pools, and also the size may still double during maintenance. But there's an interesting use case for this. I personally would say it should probably not be used for usability repository sizes because it's not flexible enough, and it still does have the issues with doubled repository sizes. But it could, for example, be used to provide a potential administrator UI to provide finer detailed or finer grained information about what the repository is state in. It will probably also get extended in the future to have additional information inside of it, like, for example, whether specific metadata is up to date or how many, or some other things. We'll probably iterate on this RPC a little bit. And then finally, object size. It has the upside that it's really very flexible, so it can only take reachable objects into account, like really reachable from a set of references. It can calculate the repository size for parts of the object graph. And it optionally also takes object pools into account if we want that. But again, it comes at the cost of being very slow to compute. So if we were to migrate to object size in the future, then it would mean that we'll probably have to refactor the way that repository sizes are calculated in the context of repositories, because right now RepositoryInfo and RepositorySize are called very, very frequently, and this would have to stop if we were to use object size. And the recommended use cases are, at least from my point of view, usability repositories, because it is the most accurate way to actually calculate a repository size. And also, if you want to check the size of parts or subgraphs of your complete object graph. So this really is like the very short primer on how repository sizes work and how repository maintenance influences the way that repository size calculations work in the context of Gitaly. Are there any questions from your side?
The utilization team has just started to use the new RepositoryInfo RPC, as you're aware. And we're using the recent size to be stored in the project statistics for a project. Every time I look at it, and even with this primer, I still think that maybe we're using the wrong one and that we should still be using size, because the number is vastly different because it's only the recent objects. And I'm not sure it's giving people or customers a accurate representation of what their repository size actually is. And my concern is that we're underbilling, or we will be underbilling for storage consumption as a result. I guess I don't really have a question. I'm more throwing out there that that's a concern I have, and whether you have any thoughts on it.
It's actually a very valid concern, and there is multiple issues at play here. The first one is giving customers an actual representation of real on-disk sizes. And that's what I had here on my summary. I think that we should actually be doing two different things. To present repository sizes to a customer, I think we should have something like a more detailed admin UI that really gives a better overview of what size the specific data structures inside of a repository have. And this is what the RepositoryInfo RPC would actually provide. So that you not only say like, okay, this is your total repository size, but we can give the total repository size. We can also give the size of the recent objects and the stale objects, as well as, for example, the number of loose references and the size of loose references. Because only giving a single number for the repository size is also not really all that informative for a customer anyway. And I would say that we should definitely iterate on that regard and give them more information about what the actual repository size is and how and what the different parts of it are. The second part that you say here is that the recent size is a whole lot smaller than the overall total repository size in the context of RepositoryInfo. And part of the problem here is that neither the repository size RPC nor the RepositoryInfo RPC actually take object pools into consideration. So that means that the total size of the repository as we report it right now is completely wrong in the first place if we have a fork, because the bulk of all the objects will be stored in the object pool and not in the primary repository itself, which means that what we're reporting as either the total repository size or even the recent repository size is a significant factor smaller than the actual complete size if you also included the object pool. But the consequence of that is that because we actually don't really account for objects at all, the total repository size, as it would be calculated based on the references and all the metadata, is going to be significantly larger or proportionally larger than the actual objects that exist in the repository, where this discrepancy comes from. If we start to correctly account for object pools in this context, we wouldn't actually have this issue anymore, because it would mean that we would include all the objects, and then the metadata on top is really only going to be a very, very insignificant fraction of the overall object size. But because we don't include the object size, it also means that the metadata is significantly larger in those repositories than the actual recent object size. Does that make sense for you?
Yeah, it does. Thank you. And I agree that we need to iterate and present more of that info to the customer. It should definitely be the next step.
Are there any further questions or remarks, comments?
Yeah, I had a question about the repo size calculation. Just curious when we actually get to a state, or how we actually get to a state where we're double counting objects.
It basically is a race condition. And the thing is, the bigger the repository, the more likely it is to hit this race condition. The problem is when you call optimize repository and optimize repository decides to repack your objects in that repository, then it could happen that when object size or repository, no, when repository size is called at the exact same amount at the exact same time where we repack all those objects into the new pack file, then we would actually have this double counting issue. So it basically happens whenever you have, or it can basically happen whenever you have a concurrent optimization of the repository ongoing. Any further questions?
Yeah, I've got one more. Sorry, I haven't added it to the document. The object size RPC, is that ready to go now? Is that live and available? Even though we shouldn't be using it because it's very slow, but can we actually use it?
It is available starting with, I think I've introduced it in Gitaly 16.2. So it is generally available by now and it can be called. Yeah, as I said, it really shouldn't be used without some refactorings of the architecture of how Rails performs repository size calculations, or at what points, because we will have to reduce the frequency of when exactly it is called. But I don't really think this is going to be much of a problem. Like, at least from my point of view, it would be totally fine to say we only recalculate the repository size at most once per day, for example. There is, of course, the edge case where the customer is now hitting the actual limits and thus cannot use that repository anymore. But what we have in the UI nowadays already is a button to manually trigger recalculations of the objects of the repository size. So if we only compute it once per day, but then also on demand when the customer has, for example, just rewritten their repository to be smaller in size, then the customer would simply go to the button, click the button, and then we would recalculate the repository size for them. And then they should be unblocked again, which again is a lot better than the current state it is in, where first the customer has to rewrite the repository, then they have to trigger repository maintenance, then they have to wait for 30 minutes, then they have to click the prune objects RPC, and then they're still not very sure whether it actually fixed the repository size, because there could still be internal references that the customer has no control over and cannot delete in any way. and that would still, for example, keep alive all the large objects in the repository. But yes, from my point of view, object size is ready to use and should also be migrated to in the not too distant future.
Cool, thank you.
Any last questions? Cool, doesn't look like it, and also we are almost on time. So thanks actually for joining the call. In case you have any further questions, I'm still very happy to actually jump into all those discussions. So definitely feel free to ping me. I will probably upload the recording so that it's also accessible to all the other folks. And yeah, thanks and see you around. Bye.